The last hydrocarbon that we need to talk about before we move on to other compounds are aromatic hydrocarbons. Remember, the aromatic hydrocarbons are based on the benzene ring. It would have been great if I had some aromatic hydrocarbons because I could have done a test with that, the same type test. But like I said, the benzene ring is a mild carcinogen, and we are not allowed to have that stuff in high schools, right? So it's unfortunate that we don't have an example. I've seen the test done using aromatic hydrocarbons, and yes, it shows us what we would expect, but I don't have any to add to it. The main thing about aromatic hydrocarbons, we might think that they're going to behave as if they have double bonds, because they do. But throughout the last couple of units, I've been talking about how the benzene ring is very stable because of the delocalized pi bonds. And that makes them unreactive. They actually don't undergo addition reactions. You can't just add molecules like we just saw to the benzene ring. It's too strong. Yep. Yeah. You can substitute them. You can do a substitution, like as if it's an alkane, but you can't do an addition reaction. To be honest, I wouldn't know how to rate it. I did not do a lot of organic chemistry in university. I don't recall. I did it in university, right? I don't recall how, put the three of them together and how quickly the other. We obviously saw the acetylene react very quickly. I don't recall. Yeah, I don't have the answer. So at this point, it's just drawing a couple of example reactions, and because this is a very short little section here. Essentially, what we're saying to you is it doesn't react like a double bond. It doesn't behave like double bonds. And that's because of that delocalized pi bond. It makes it strong. Okay. So what we're seeing here is an example of halogenation, an addition reaction of the benzene ring with bromine, and it will actually do this twice. So I'm going to put here a 2. And in the end, we end up again with 2, in this case, HBr. It's not that each bromine gets added in, right? An H comes off and makes an HBr. Yep. They actually will always go in the pair, what do we got here? Meta position. So in this case, we do want the meta position. Meta position is favorable. So the favored product, 1,3, what we're really saying here is meta is favorable. Memorize it. How do you know? Remember when I was babbling on a moment ago in that book about favored this? That book tells you why and how and all the good stuff. We're not going to worry about that. You're just going to memorize that 2 of them will add and they'll go into the meta position. And you'll learn someday about why. And I could look that up later. I might actually read it later. I might. I don't know. We'll see. That I might not read it, I'm sure that's the favored product, that I might not read it. If I give you a question to do on a test, this is a memorization spit back out situation, right? I could give you any of the halogens, but you'd just put the 2 of them in the meta position, right? So any halogen could go in there as a valid test scenario. Now there are other things that you can add readily to a benzene ring, and the next one is a nitro group. Oh, goodness. And I'm going to draw this one on. So you can actually react nitric acid with a benzene ring. And I'm going to show you as soon as my pen starts working again. The reason we're writing it in this way is because what happens is an OH, this molecule looks like this. Actually, we had this molecule on our last test, right? That's what I wanted you to draw the Lewis structure for, right? Now, I don't have all the electrons in there, but there's obviously a structure there. And this structure actually has a resonance scenario that looks like this. Actually, I will draw the rest of the electrons in. It has a resonance situation that exists between these 2 O's. I can put the double bond to the other one. What happens is that OH falls off, okay? And it becomes a water because it plucks off one of these. And it gives us this situation here. And I'm going to add 2 of them to it. What am I doing with my benzene ring? That's a horrendous benzene, but anyway, you get the idea. Put a double bond there, put a double bond there, put a double bond there. And you end up with an N, yeah, it's a sad one. Yeah, it's a sad benzene. You end up with an NO2 over there, and you also end up with an NO2 over there. And actually, the resonance of this NO2 feeds into the benzene ring. It actually, the delocalized pi bond goes all the way out into the N's and the O's as well. It actually makes it stronger. Anyway, this is nitro. So that group here is nitro. That's called a nitro group. It's going to be 2. So what do we have left as our other product? Oh, sorry, 2, yeah. This is also 2H2O, okay? And the name of this is meta-dinitrobenzene, or 1,3-dinitrobenzene. 1,3-dinitrobenzene. All right? 1,3-dinitrobenzene. Add another nitro group, and add a CH3 group, and you've got something that's called 1,3,5 trinitrobenzene, or sorry, it's actually trinitrotoluene, and that's what TNT is. TNT, the explosive, is a nitrated benzene ring. It's got a couple of extra things on it. It is TNT, yeah. I don't have enough time to do this one right now, so we'll come back and do that, and I'll give you these. Yeah, there's a lot of it today. Yeah, yeah. Take your biology and you can apply it to there. In university, you get into more reasons on why, right? Here we're just learning the basics. Yeah.